Okay, so we start the next session. So the speaker is Professor Rajesh Gopakumar. He is going to tell us about aspects of higher spin theories.
So thank you very much. I'd like to thank the organizers for putting together such a very nice school with an exciting program. And so I hope you're enjoying it. I realize you probably are quite tired, and today is a packed day. And higher spin theories are not have a reputation for being technically taxing. So I will be talking about higher spin theories in AdS 3, which is in some sense the poor man's version of Vasilyev's equations in general. And I hope it will be relatively less taxing. So you've heard already, Sandeep just tells me also that you've had already some exposure to higher spin theories in Spencer's lectures, but it will be somewhat complementary being in 3 dimensions. I will with all the motivations and other things, because again, Spencer probably has talked about that. But one of the reasons to concentrate on this poor man's version is that, and which I will try to convey, is that there are many things you can very concretely do with this particular case. It's difficult in the higher dimensional case so far, and one might hope that being able to concretely do this, and one is learning quite interesting things from the dynamics of these higher spin theories in 3 dimensions. From these, we might be able to transfer these to the higher dimensional case. So that's the idea. So the primary simplifications in 3 dimensions. So simplifications in 3 dimensions are primarily due to the fact that the higher spin theories, the higher spin gauge fields, have no propagating degrees of freedom, just like gravity in 3 dimensions. So it's not very difficult to convince yourself that basically, if you look at the little group of the in 3 dimensions, it's quite trivial. So the massless fields, which transform under the little group for massless particles, is trivial, and you essentially have no propagating degrees of freedom. You can do it a little bit more elaborately, counting the gauge degrees of freedom and the number of tensorial degrees of freedom, but it's sort of similar to how you do it for pure gravity in 3 dimensions. So this means that they are sort of essentially topological, but at the same time, just like 3-dimensional gravity, they have interesting solutions and so on. But large class of interesting solutions. In fact, the higher spin theories have many solutions which large classes of solutions which even 3-dimensional gravity normally doesn't have. So of non-trivial solutions. So in addition to the sort of BTZ black hole-like solutions, there are several others, and I'll say some of that, describe some of that later. And related to this, major simplification in 3 is that the higher spin spectrum can be truncated to spins which go from 2 up to some maximum number n, which is not possible in higher than 3 dimensions. The Vasilyev equations necessarily involve an infinite set of higher spin fields. So these are 2 major simplifications which help you to deal with the equations fairly tractably, as we will see. But at the same time, they carry many of the conceptual, many of the conceptual questions you can ask about the meaning of these higher spin fields and so on can also be asked in this. So even though, so they capture many essential aspects while being simple. So that's a good reason to study them. So this thing is not possible for higher spin theories in higher than 3 dimensions. Well, the higher spin algebra does not close. There is a gauge algebra which is, which if you, basically, it does, if you have spin 3, then you're forced to, for the closure of the algebra, you're forced to include a spin 4 and so on, and there's no way to truncate it here. Because there are no propagating degrees of freedom, it's possible to truncate it. And we'll see explicitly what the truncation is. So to sort of warm up with this, we'll start with 3-dimensional gravity itself, this so-called Chern-Simons formulation, which maybe many of you have seen, but in any case, we'll review some aspects of it which will be useful, which will carry over to the higher spin case. So this is the SL2R times SL2R formulation of 3D gravity. Which is due to Achukaro and Townsend and Witten. Well, 3D gravity in AdS3, but there's a similar formulation in flat space, de Sitter space, etc. So this starts from the frame formulation of gravity. So in the frame formulation of gravity, we have, and indeed the Vasiliev theories in higher dimension are always formulated in the frame language. It has been very difficult, and in fact, it is not known how to formulate it in a more metric-like language. So by frame language for gravity, I mean the field binds. So in 3 dimensions, so A goes, these are the tangent space indices, which will take to be 1, 2, and 3, and these are the coordinate space indices. So the tangent space and the coordinate space as usual, and the metric is given by the usual, so the G mu nu is just the E mu A, E mu B. And the indices are raised and lowered with the tangent space metric, which in this case is the SO2, 1 eta AB. So in the frame formulation, you have these field binds, but you also have a spin connection which carries, which are two antisymmetric and two frame indices and the tangent indices. But the nice thing in 3 dimensions is that you can write this as equal to, you can trade this for a single index object, and the important observation, is that these two, namely E mu A and omega mu A, can be combined into two SL2R gauge fields. So you define 2 gauge fields which are SL2R, because SL2R is the same as SO2, 1. Indices A essentially are 2R or SO2, 1 indices. So you combine them into these 2 gauge fields because the gauge, this is minus. L is the AdS radius, or 1 over L square is proportional to the cosmological constant. The reason to combine it in this way is that the conventional equations that you write in the frame formulation have a nice form when written over here. So the conventional, the frame equations of motion, the frame equation, I mean in this frame language, the equations of motion for omega A and EA. By the way, sometimes I will, you can view each of these as one forms. So sometimes I'll just drop the mu index, and then what I mean is that there are one forms. So let me write it out. EA is just EA mu dx mu, etc. So the frame equations for these are the ones in which the first equation is the one which determines omega, which is the so-called torsion equation, which can be written in terms of So this is, you can view this as an equation which enables you to solve for the spin connection. You set the torsion is defined this way. So you set the torsion equal to 0, and that determines omega in terms of E to be equivalent. Omega will be the Levi-Civita connection. So that's one equation of motion. And there's a second equation of motion, which is to do with the curvature of the spin connection. And that can be written as, so I'm just writing the conventional gravity in 3D gravity of Einstein gravity with a cosmological constant. This frame language, the corresponding equations of motion are just so that's this is basically the frame formulation of that R mu nu is cosmological constant times G mu nu. This is the version of it in this frame language. So these two equations of motion, which are your conventional, when you express it in terms of this A mu and A mu tilde, become very simple. So in terms of A and A tilde, they just become and similarly for the A tilde, they separate very nicely. So basically, you add and subtract these equations, or you start here and you see that if you add and subtract, you get these using this definition of A and A tilde. So what we have done right now is rewrite Einstein's equations in terms of these these equations are in terms of an SL2R gauge field, they are essentially the statement that that the field strength is the field strength of this SL2R connection. So both these field strengths are 0. So this is a very simple equation. It's telling you that A is what is called a flat connection, and these equations of motion, you probably know, these follow from an action, from a Chern-Simons action. Chern-Simons functional is precisely the one whose variation gives you these flat connections. So to be precise, the action can be written as in terms of Chern-Simons functionals for both A and A tilde. So let me call this K hat. So this is the Chern-Simons functional, ADA plus 2/3 A cubed. And this is what is called the level, K hat, which I'll define in a moment. So of course, each of these functionals, when varied, gives rise to these equations. So the relative sign that I have put here is determined by parity. The fact that the original Einstein theory is parity invariant, and you can see from the definition that under parity A and A tilde are essentially interchanged, and therefore the relative sign is fixed to be this -1 sign, the absolute coefficient, this K hat, is fixed by comparing the Einstein action, and in fact, in the Einstein action, conventionally normalized, you have a 1/16 pi g Newton outside and related to K hat. So if you compare it to the Einstein action, what you find is that essentially K hat by 4 pi is, or wait. So K hat is basically L over 4 times the Newton's constant, the AdS radius. So it's a dimensionless quantity, and it's called the level of the Chern-Simons theory. So this is the formulation of the of three-dimensional gravity in terms of gauge fields, in terms of Chern-Simons gauge fields. So, so many of the things that you have probably seen about three-dimensional gravity can be rephrased in this language, and are actually somewhat simpler. So in fact, one can look at the most general solution of these equations of it's in a way quite, these are flat connections as we just described, field strength equal to 0. So they at first sight you might think they would be just trivially gauged, but because you have to be a little careful because you have to impose boundary conditions on the gauge fields, and so it turns out that there are some boundary degrees of freedom. So this is the essential reason why three-dimensional gravity is logical. So there are no bulk degrees of freedom associated with this, but there are some boundary degrees of freedom nevertheless associated with this. And the way it sees it is okay, I'll just summarize very quickly how what the sort of general space of solutions are for this of these equations. So they are, as I said, pure gauge, and so you can the physical asymptotically yes. AdS3 solutions. So of course, AdS is a solution of the Einstein equation with a cosmological constant, and there better be a gauge connection corresponding to that, which is a solution. I will write that down as a special case of the most general solution. So what I will write down is the most general class of asymptotically AdS3 solutions of these equations of motion. So these include BTZ black hole, including BTZ black holes, and more generally more general solutions. And these are given by a family of flat connections. And to see that, it's useful to it's useful to actually take out the radial dependence. AdS3, so AdS3, you probably know, is sort of like a cylinder. So it's three-dimensional space, solid cylinder. And if we choose sort of rho as a radial coordinate, phi as an angular coordinate, and time as the vertical coordinate, to parameterize AdS3, then it turns out that you can write these asymptotically AdS solutions in the following way. So, and it will B is a matrix which carries all the radial dependence. So rho is the radial coordinate, and L0, so let me define now the generators of SL2R, which we conventionally use. So L0 is essentially half times sigma 3, the Pauli matrix, and then to define L1 to be, in our notation, just sigma plus, which is basically 0, 1, 0, 0, and 1 to be minus sigma minus. So that's 0, 0, minus 1, 0. Yeah, so there's a family which I will just mention. So let me define this family. So firstly, it's possible to remove the radial dependence by this overall gauge. Use the freedom of gauge transformations to remove overall radial dependence, which is also a reflection of the fact that there is nothing really in the bulk. So the Z and Z bar are essentially the complex coordinates on the boundary, phi plus IT and phi minus IT. D over L in appropriate units. But so this family, I have, so you see the radial dependence is completely fixed. You can have these A of Z and A bar of Z bar, which are on the boundary, which you can view as sort of specifying data on the boundary, and these take the following form. And similar, A bar of Z bar is equal to L minus So, so the general asymptotically AdS3 solutions one can show are essentially, so one has to work out what the one has to use the freedom firstly to pull out the radial dependence, and then then of course the A of Z and A bar of Z bar are also flat connections, and have to be flat connections to satisfy the equations of motion, and if you can use all the residual freedom to put it into this form, where L1, L minus 1, 1 are these generators of SL2R. So, oh, sorry, I should have said this is just DZ and this is DZ bar. So this one has, so these are one forms. So it has only a DZ component, and this has only a DZ bar component. So, and these L of Z and L bar of Z are arbitrary functions. At the moment, they are arbitrary functions of their arguments. They are holomorphic. This one is purely holomorphic, and this is purely anti-holomorphic. And in fact, from a more modern perspective of AdS CFT, can be identified values of the stress tensor, the holomorphic and the anti-holomorphic components of the stress tensor. And that's not difficult to verify. It's a small exercise which is quite instructive. To do, and in fact, it enables you to read off in this formulation the classical Brown-Hainaut central charge. So you have probably heard that in 3 dimensions there is the asymptotic symmetry algebra is a Virasoro algebra with a certain central charge, and one can read that off by Chern-Simons formulation from these solutions in the following way, that these, so this is, if you wish, the parametrization of the classical phase space of solutions, and these solutions, you can ask how, I mean, what are, how do under a gauge, under gauge transformation, which preserves this form of the solution, how does it transform? So you can ask, look at the residual gauge transformations which preserve, so you have this A of Z and A bar of Z bar. There are some residual gauge transformations which preserve the form of this of these connections, except that they change this L of Z. So the residual gauge transformations are also parameterized by, so I'll maybe write this as an exercise. So verify this gauge transformation lambda. So this is, of course, the transformation of a gauge field under an infinitesimal gauge transformation with lambda being equal to the inverse some lambda of Z B, preserves the form of the classical solution if lambda of Z takes the form some epsilon of Z L1 minus del Z epsilon L0 plus half del Z square epsilon minus 2 pi by K. this transformation, you can verify that the form of the classical solution is preserved. Only thing is L will change, and the way L changes, so you can view this as some kind of a holomorphic gauge transformation, because this is valued only on the boundary, depends only on Z. If you wish, it's a gauge transformation parameterized by this epsilon. And under this infinitesimal gauge transformation, this gauge connection transforms to this A plus delta, in which the L has changed exactly as the tensor would under an infinitesimal diffeomorphism. So so it's 2 del Z epsilon into L. And then the important part is this is additional piece, which is the piece, the inhomogeneous way in which the stress tensor transforms. So these are basically telling you, this 2 is telling you that it transforms like a 2 object, but this is the piece which is telling you that additional central term, and translate this, you see the Brown-Henno central term. Sorry, these are all these k hats. Wherever these k's appear at this stage, they are all k hats. And so from this you get the Brown-Henno central charge, which is equal to 6k hat. So is equal to. So this is an alternate way in which you can obtain the Brown result that this. So you learn two things from this exercise: that this L of Z behaves like a stress tensor boundary, and that it has a central charge which takes this value, and that's why these theories are dual to two-dimensional CFT with central charge, which is related to 1 over G Newton. Okay, any questions? So.
What is the asymptotic symmetry here?
Asymptotic symmetry?
Symmetry group.
Yeah, it's the two copies of the Virasoro, because there is the L of Z and the L bar of Z bar has similar transformations. Both have the same central charge. So you have two copies of Virasoro, left and right, moving Virasoro algebras with the central charge. So at least in the pure gravity case, we'll see later that the asymptotic symmetry algebra can be bigger.
So you said, so because there is no degree of freedom, I can make it transversal and make it J independent, right? I mean the radial coordinate independent.
I mean, it's not independent, but yeah, you can. In fact, when you put this pattern over here, you will see that the metric is really an asymptotically AdS metric. In fact, I should tell you in a moment what value corresponds to AdS3 and VTZ black holes. But yeah, so it has a definite radial dependence, but the radial dependence is fixed.
And so the C that I get from here is this. I mean, how do I interpret from the bulk point of view? So these are the degree of freedom at the boundary as you.
Yeah. So you should view this. So this is essentially saying that the classical solutions which parameterize the degrees of freedom of the system are essentially only on the boundary. I mean, on some radial slice which you can take to be the boundary. So they have only a one-dimensional lower worth of degrees of freedom. You can view these as what are called boundary gravitons. So you can have arbitrary excitations, left-moving, right-moving excitations on the boundary, So they have the degrees of freedom of a two-dimensional CFT living on the boundary. So that the theory is essentially topological, but for these degrees of freedom. So I should tell you what corresponds to 3 BTZ black holes, etc. So in fact, when you just take these L of Z and L bar of Z bar to constants, so you take L of Z to be some constant L, which if you parameterize by an L bar of Z bar, this is, if you take these, but not equal to L, so this is defined to be so you have, if you have 2 constants, then if you write down the corresponding connection, and put it in over here, you'll get radial dependence. In fact, let me just write down for you what the A and the A bar look like. So A looks like e to the rho L1 minus 2 pi by and that is so if you take A and A tildes and write down the metric, so remember A and A tilde, the sum of these, the difference of these is proportional to the field bind. From that, from the field bind, using the formula relating the metric to the field bind, if you write down the metric, you will get the BTZ metric. If you put a BTZ metric of a black hole with mass m and angular momentum j, if you take L and L, these to be constants parameterized in this particular way, and so that's the particular case. Global AdS is a special case when, so global AdS corresponds to the AdS3. This corresponds to the m having particular value, which is minus 1 over 8 g Newton, and j equal to 0. So this is the frame formulation of the 3-dimensional gravity. All the results that you may have seen before can be fairly simply derived in this language for the BTZ black hole. There's the thermodynamics of the BTZ black hole also has geometric interpretation, which will be useful when we generalize. I'll just mention that before.
But they are not complex,
No, they are not necessarily complex conjugates of each other. Yeah, the notation is a little misleading. They are not necessarily complex conjugates.
Just erasing that equation of A and A bar.
Yeah, they are A and A tilde are independent gauge fields. So these are not complex coordinates. Yeah, you should, maybe I should have used A tilde also for this. this is a sort of a non-geometrical formulation, but that's so the advantage is that you have some of the gauge theory intuitions about flat connections and so on, but we lose in this frame formulation, we lose the sort of metric-like interpretation, but the gauge interpretation in Chern-Simons language actually provides a good guide to understanding of the three-dimensional solutions. So in particular, I just want to mention one thing that in these theories, there are no local, because the connection is flat, the field strength is 0, and therefore there are no local gauge invariant observables, like powers of the field strength, etc., are all 0. But there is a non-gauge invariant observable, which is the Wilson line, or the holonomy, namely the trace of the path ordered. This is a gauge invariant, so around a closed loop. This is a gauge invariant observable, and similarly for A tilde. And in these geometries, which correspond to the BTZ black hole, one can look at the time-like circle. In the typical way in which we derive the Hawking temperature for black holes in a Euclidean setting is to look at the time direction circle, which has a periodicity of the inverse temperature, and we demand that this circle, which shrinks to 0 size at the horizon, have no conical singularity. That's our conventional Gibbons-Hawking way of obtaining the temperature in terms of the mass and other parameters. Here we have a solution parameterized angular momentum. How can we, in this formulation, without reference to this conical singularity prescription, how can we find the thermodynamic relation between the temperature and chemical potential for angular momentum and these objects? And the way we do it is through these holonomies. So these holonomies, on a contractible circle, like the time-like circle, for a black hole. So these holonomies on a contractible circle must be trivial. So because this is a Chern-Simons gauge field, so it doesn't matter where we evaluate it. So in particular, you can so if you have a circle which is contracting, you can evaluate the holonomy here, or you can evaluate it here because the connection is flat. And in particular, you can evaluate it on a very small circle near the place where it pinches off. And if this point is to be regular, if there is supposed to be no concentrated strength, delta function of the field strength, which is another way to talk about the curvature, conical singularity, if there is to be no singularity there, you want this holonomy to be trivial, meaning it should be an element of the gauge group which is trivial. Normally this might mean the identity element, but you have to be in the general gauge theory. It can be somewhat larger. It can belong to what is called the center of the gauge group. All the elements which commute, with everything in the gauge group. And in particular, let's see what that condition. Yeah. Okay.
Just to understand, are we talking here about Euclid?
Yeah, I started with the Minkowskian, but now I have moved over to this thing. The expressions are very similar. One could have, so at the stage where I wrote down the connections in terms of Z and Z bar, I had moved over to the Euclidean language. Otherwise, I would have had to write it as dx plus dx minus. Okay. But you're right. I sort of glossed over that. But yeah, so for now, let's stick to the, because what we are doing is the analog of the Gibbons-Hawking computation. Yeah.
So just on this, so here, so you said that wherever I compute, it should not matter where I compute, right? So it just does not just follow from what you saw that it's everything independent of radial coordinate system.
It follows from the fact that the field strength is 0. So if it's a flat connection, if I deform it, so the difference between these two would have been proportional to the flux through this. So that's 0.
So if I have a black hole, so black hole meaning now I do the transformation as you saw. So everything I can make it radial independence, right?
Yeah, it's not radially independent. That's a way of parameterizing it. The actual gauge field has a radial dependence, but which is fixed. Yeah. So this is rho is the radial coordinate in a certain Pfefferman-Graham-like radial coordinate. So there's a radial dependence, all right. I mean, the BTZ black hole has a radial dependence, but it's a prescribed radial dependence. Yeah, so it's not completely, that's why I don't, it's best to think in terms of the gauge invariant notions like the connection, which are, and not so much about radial dependence or independence. So in this BTZ black hole, so as I said there, the time direction would be, time direction is a contractible cycle, so you want this holonomy to be trivial. The holonomies along the time circle are e to the 2 pi tau az. Well, so in this case, only z component, and similarly e to the 2 pi tau bar a bar bar, because the holonomy just the holonomies are equivalent to this. There was the B inverse AB, but that comes out, and well, actually, sorry, this is indeed a gauge invariant observable, but when I talk of the holonomy, by that I mean just by that I mean without the trace, the matrix, which is the path ordered exponent. So this must be trivial. So these and in the case of in the BTZ black hole, so in the Euclidean theory, as Sandeep rightly pointed out, we are now in Euclidean language. The time-like direction has a periodicity tau, which is related to the inverse temperature, and the holonomy matrix is related to basically this, because it's A of Z, the factors of B inverse B are just similarity transformations. So we'll actually be interested in eigenvalues of this holonomy matrix, so it will be sufficient to consider. And so its eigenvalues, so if you just look at the A that I had written down, which I have rubbed out, but for these constant for these for constant L and L bar, the eigenvalues are just e to the plus minus square root of 8 pi cubed L over k hat into tau. This is for this, and there's a similar expression for. So there are two eigenvalues. There's a 2 by 2 matrix, and its eigenvalues are just this. It's a diagonal matrix. Sorry, it's not. So A of Z is not a diagonal matrix, but you can diagonalize it and find its eigenvalues, and they are just equal to this. And so demanding that it is trivial, that it is trivial gives you actually, well, there's one solution where you can demand that it is one identity, in which case you get a trivial solution. You get that these should be, tau should be 0, but but there's a non-trivial solution where you have e to the I pi and e to the minus I pi. This is minus 1, but it's a trivial element because of the identity commutes with the all elements of the SL2R. So if you demand that these are just this tells you that basically this exponent is equal to pi, and that gives you exactly the thermodynamic result that tau, which relates tau to the tau to the mass and the angular momentum. So it gives you something like 2 pi. So this is the, and similarly for tau bar, this is exactly what you get for using conventional analysis that you would have done with the beta black hole metric, but now done in a gauge invariant way in terms of these holonomies. So is this clear that what we are doing is a sort of an alternate way of obtaining the black hole thermodynamics of the 3D black holes from this Chern-Simons language point of view, and this will be useful when we generalize to higher spin theories. And the basic observation is that because these are the only invariant observables, and they should, in some ways, they capture most of these features of the theory, and in particular, demanding that along a contractible circle, these holonomies must be trivial, fixes the temperature in terms of the mass, temperature, and chemical potential, because tau and tau bar together determine the temperature and the chemical potential. So those are determined now in terms of M and J, but in this non-geometric way. Okay, is this clear? If there's any question, because this is an important point in the generalization, and it's not conventionally done this way. So if you are uncomfortable with some aspect, just stop me.
So what happens to the other values? Like in general, you could have e raised to I n pi, right?
Yeah, so it's a good question. So you could have had so we'll see later that you can have more general. You could have had more general solutions in at least the SL n cases where indeed the holonomies can take on more different values, but in this SL2R case, I think I mean, I don't see any physical interpretation for the solutions which have these higher values of e to the, say, 3 pi or yeah. So there is probably something that restricts you in the range minus pi to pi, the whole in this range, but so those don't seem to be valid solutions. At least they don't seem to correspond to any solutions I can yeah, I mean they are, so the gauge element is the same because it's -1, -1. So the gauge element is the same, but the holonomy is different. So that's why I think you should really restrict to the range minus pi to pi when we do this. But yeah. So I think that there's probably you probably need to restrict it to that to that range. Except that in the higher, the only reason I'm a little bit hesitant about that is that in higher spin cases there are which, but they are also sort of surpluses. They have deficit angles which are sort of multiples of 2 pi. So they are probably they are probably unphysical in some way, but yeah. So I'm not sure what global constraints there are to rule out these solutions, but I think at least in this SL2R case, the holonomy should be in this range minus pi to pi, and that is what gives you the conventional black hole thermodynamics.
It would just mean you go about the circle more than once.
Well, it's not, I mean, the holonomy is really the same because it's still -1, -1. It's more a sort of a shift by, I mean, so it's a little bit ambiguous how we define this. So you could probably view it in the metric language as there being some sort of conical surplus, which is a multiple of 2 pi n. So which normally you don't consider. So it is probably the analog of that, where the deficit angle is not 0 or 2 pi, but it is something like a multiple of 2 pi, a larger multiple of 2 pi. Yeah.
So these are classical solutions so far you're telling us.
Right.
But at some point will you tell us what happens when you try to quantize them, or is that
in the Chern-Simons theory, the SL2R Chern-Simons theory does not seem to admit any sensible quantization which gives you the results which you might so you would require some kind of a unitary CFT on the boundary to arise as the result of this quantization, and that does not seem to be the case. If you naively try to quantize it, you seem to get some kind of a Liouville theory, which this Brown-Henno central charge. So it does not seem to have the states really that go with the unitary CFT. So just a naive quantization of this 3D gravity or even the higher spin versions of them don't seem to work. You probably need to embed it in a string theory which would give in which this gravity would be a subsector. And so, yeah, so I think the quantization of this would need an embedding into a larger theory. There is probably no quantization of pure gravity as such. Yeah, so identity would have been, would have given you something where tau is equal to 0. So that's one possible choice, but that, in fact, but that's corresponding to sort of a 0 temperature or so that's not something which so you could have taken that, but this -1 is also an element of the center, and that's what that's what seems to describe a thermodynamic quantity object, which you have a temperature which is determined in terms of this mass and the angular momentum. So yeah, so for it seems to be a non-trivial element of the center of the gauge group and not the trivial element. Sorry? So so the other one doesn't seem to give you any sensible thermodynamical quantity. So yeah, so there are some additional constraints which we will see on this that you have to put for it to have so we'll see later in the generalization that this holonomy constraint, it's only for certain values of the holonomy in the center that you really obey all the thermodynamic constraints that the theory if has to obey. For instance, these should all follow from a partition function, and that this temperature mass relation should follow from a partition function. So this is not completely guaranteed by what I have said, and that will be a condition that we need to impose. So I'll just quickly mention the generalization and then stop. I guess okay. Okay, so I'll just take a little bit time. Okay, so this was in some sense a review of three-dimensional gravity, but so the generalization to of the SL2R formulation to SLNR describes the higher spin theories with spins 2, 3 up to n. And so let me describe that you a bit. So this actually, when I say that the general you are describing these higher spin theories with these spins, it also I'm also implicit that the SL2R is the SL2R of gravity is embedded in the SLNR in a particular way. So in the so-called principal embedding, so what I mean by this principal embedding is the following. So if we take JA as the generators of SL2R in the n by n representation. So earlier I was writing the SL2R generators in the 2 by 2 representation, the fundamental representation. But just like SU2, I mean SL2R is just SO2, 1, so it's sort of it's essentially like SO3 or SU2. So you can write the generators in an n by n representation. Just like you do for SU2 or SO3, and then if one constructs DAB, which is just JA, JB. So this means symmetric and traceless. So you take JA, JB, then define again TABC, which is JA, JB, JC, again symmetric traceless on these indices, all the way up to TA1, AN-1, which you define in the similar way as built from these matrices. Then it turns out that these are by construction, and they don't obey any relations between them, because J is an n by n, and so these, it turn out, are all independent matrices, and these together, these form a representation of the SLNR generators. So because SLNR is generated by n traceless matrices, so it turns out that there are precisely n square minus 1 of these if you just do this counting, because JA there is 3, and here symmetric traceless there will be 5 and 7 and so on up to 2n minus 1 in this. So this is essentially equal to n square minus 1. So the principal embedding is precisely the one in which we realize the SLNR generators in terms of the original SL2R generators by in which the SLNR is SL2R is embedded the SLNR by construction, and so you see that so it's, if you wish, also a way of saying how the different generators decompose under the SL2R. This decomposes a symmetric spin, symmetric second rank index, and this has a symmetric third rank object, so on. So, so the claim is that, so I'll now justify the claim that suppose we embed SLR inside SLNR by this kind of relation. The generalized, the elements like generalization I described earlier will describe a gauge theory of higher spin fields with spin up to n. So any questions about this this simple embedding? I'll just 5 minutes and just describe what the SLNR theory is and then stop. So So for that, let me just focus on SL3R, because after that, the things will be sort of simpler. So in that case, we are looking at 3 by matrices. So we have JA, and we have this TAB, which is something like JAJB. So there's 3 plus 5, 8 matrices. And so again, consider now A and A tilde, which belong to SL3R. So each of these are 2 independent connections. Define these to be omega plus E over L and omega minus E over L. But now, so now the difference is that omega is equal to omega mu A JA plus omega mu AB TAB, and E is similarly E mu A JA plus E mu AB TAB, and then whatever dx mu. So in addition to the field binds, we have additional fields. So in addition to the earlier spin connection and the field binds, we have additional fields now which transform, so which carry 2 indices. This is symmetric indices in the AB. And these are precisely so these additional ones. So these are, of course, your familiar gravity, I mean the fields associated with gravity, but these turn, so the E mu AB can be thought of as a frame formulation, frame form of the field. Because you see, at least at the linear level, you can define something phi mu nu lambda, which is E mu AB E bar nu, well, E mu, let me put it AB E nu A lambda B, where these are the background AdS3 field binds. So basically, indices. So you can get in 3 objects from this. There will be an analogous spin 3 connection, and so that's the underlying reason why I can show that this has the linearized equations of a spin 3 gauge field. Moreover, the gauge transformations are now belonging to SL3R as well. In addition to the SL2R transformations, which generate the usual Lorentz rotations for the field binds, you have an additional spin 3 gauge transformation, which are the generators, so in addition to the additional gauge transformations, which are of the form some lambda AB, TAB. So this you see is again a sort of a second rank X gauge parameter. So it's linearized level. It's like phi mu nu lambda plus some del mu lambda nu. So if you trade this for coordinate space indices, again using the background field binds, you see you have an additional sort of a spin 2 like gauge parameter. So these additional gauge transformations are ones which act on the spin 3 field, and moreover they also act on the spin 2 field. So this bigger gauge group is acting on both the spin 2 and the spin 3 fields and sort of mixing them up. And that's the characteristics of these higher spin gauge invariances, that that one has a mixing between the gravity field and the higher spin fields, and that's why diffeomorphism invariants or quantities which are diffeomorphism invariant are not necessarily invariant under the full group of gauge symmetries, which is larger. So let me maybe stop over here, and I'll pick up